So in this video, we're going to talk about adding vectors together. And before we do that, you want to make sure you know the basic terminology about vectors. A vector is something with magnitude and direction. It's a more complicated idea like force. A force will have a magnitude, a how much, like 15 newtons, and a direction. If I'm picking something up, the direction of that force is going up. The magnitude of a vector is sort of symbolized by its length, and this is the sort of symbol for it. And also, the magnitude is just the how much. It's just really a number. It doesn't really have a sign on it, and because it's just a number, people like to say it's always positive. So just a quick vector review for you from the last video. Okay, so let's say I wanted to add these two vectors A and B to get some vector C. Now note, in this case it's not as easy as doing 7 plus 10. Vector addition is not that easy, because a vector is more complicated than just a simple number. Remember, a vector is, in a sense, two numbers. You got a magnitude, a length, and also a direction. So you can't just simply add. This is adding numbers. This is adding scalars. But here's how I like to think about vector addition. If I have 3 apples here, and then I put 2 more on top of it, as a whole, I now have 5 apples. I treat all these apples as one unit, and there's 5 of them. That's how I kind of like to think about vector addition. I start with my first vector, that's my A, and I draw it. And then, where A left off, I continue drawing the second vector, B. And then as a whole, the sum will be from the very beginning to the very end. So this is my C. This is my sum, also known as the resultant. So here's a new word for you. The resultant just means the sum of 2 or more vectors. And just like 3 and 2 make 5, I can also switch it up. Addition works like that. 2 plus 3 is also equal to 5. Same thing with vectors. If I do B plus A, it'll get me that same resultant, C. So check it out. If I wanted to start by adding or by drawing B here, so here's B, and I sort of extend from B with A, I'll get that same C. The resultant is always drawn from the very beginning to the very end of your last vector. So because of this method, this way of adding vectors is known as the Parallelogram Method of adding vectors. Now another name for this method is tip-to-tail method. So if you look at any vector, this is the tail, and this is the tip. So let's say we were doing A plus B again. My A is right here. This is the tip of A, and notice how I place it right with the tail of B. So I'm placing the tip of A, I draw A, and here's A's tip, then I continue drawing the tail of B up until the end here. So another name for parallelogram method is tip-to-tail method. They're just two different words that really mean the same thing, the same technique of adding 2 vectors. And this parallelogram method tip-to-tail thing also works on adding more than 2 vectors. You can add 3, 4, 5, whatever vectors using this technique as well. So let's say I wanted to add these 3 vectors, C plus B plus A, to get some resultant D vector. I would do the same thing. Start with my first vector, C. I put its tip to the tail of the next vector, B. And then I just continue off B to draw A. And then the resultant, the sum, is basically the whole thing, the whole structure, from the very beginning through the very end. And I have a practice video where we work out the math of doing a parallelogram method between two vectors. You can actually put some math to this and figure out the magnitude of your resultant and your direction, that angle of it. Okay, so parallelogram method is just one way of adding vectors together. The other way is known as component method. So before we talk about component method, another way of adding vectors together, we of course have to talk about what a component is. This is a very important concept. So components are just smaller vectors that add up to get your main vector. So in this case, if I look at my vector A here, this little mini vector here, that's my x component, and this smaller vector here is my y component. These are two smaller vectors that add up, notice that parallelogram tip to tail adding there, to get my main vector A. So if I do my trigonometry here, cosine to find that x and sine to find my y, I'll get 4.33 as the length of my x component and 2.5 to get the length as the length of my y component. And I can represent my vector A in the form of its components. I can say that A vector will have an x component of 4.33 and a y component of 2.5. Now, we got some new symbols going on here. This is known as I hat. This is known as j hat. These are what we call unit vectors. We won't address them in this video. Just think of this thing as, in a sense, the x and y coordinates of my vector A. In a sense, I can represent a vector with its magnitude and direction. This is kind of like polar form with its hypotenuse, 5, and its angle theta, 30. But I can also represent a vector with its Cartesian equation. Really, this just says that vector A has a x-coordinate of 4.33 and a y-coordinate of 2.5. But the way we're saying it now is that vector A has an x component of 4.33 and a y component of 2.5. And again, we'll kind of dig into this vector equation in another video, what this I hat and j hat thing is and why is there a plus there. But know that components are just smaller vectors that add up to get the main vector. They are components of the main vector. So our components of A is our smaller vector here, our x component, and notice how it does that parallelogram adding with our y component here to get our main vector A. So let's say I wanted to add vectors A and B. Not using parallelogram method this time, but component method, now that we know what components are. The component method of adding vectors together is actually really easy. All we do to get our resultant, our C, is to add the x components of our vectors together and then the y components of our vectors together, like this. So my resultant, my sum, C, will equal 4.33 plus 2.12, 6.45 in the x, and 2.5 plus 2.12, that's 4.62 in the y. It's as simple as that. This is the Cartesian vector equation, Cartesian vector form of our resultant, C. And I can draw a picture of C based on this. It's going to have a pretty big x component, that's that 6.45, and its y component is that 4.62, and these components add together to make our C vector. So that's how you do component method. It's as simple as adding the x components together to make the x component of your sum, and the y components together to make the y component of your sum. That's it. Okay, and I just have one more thing to show you, and then we'll be done. I want to show you how similar parallelogram method and component method are. They're literally just two different ways of doing the same thing. Let's do a plus b again, but we'll do the parallelogram method. So I'll draw my a, and I'll continue off it with my b. It's a little steeper at that 45-degree angle. And of course, here is my c. I just did parallelogram method. Here's my c. Here's a picture of it, and we can do math to figure out the length, the magnitude, as well as the direction. Well, check this out. Here is the x component of A. Here is the x component of B. And this whole length right here is the x component of C. So you can see just by this parallelogram picture that if I add up these two lengths, I'll get the length of my x component of my resultant. And same thing with the y's. We can visually see the component method at work here in our parallelogram picture. If I add up these two y component lengths, I'll get the total y component of my resultant c. So I just wanted to show you guys that parallelogram method, component method, they really go hand in hand. Parallelogram method allows you to draw a picture of your resultant very quickly, and component method lets you get those numbers, lets you get the math of that vector c very quickly. But they're really two different ways of accomplishing the same exact thing. So that's it for this video. Check out the practice videos to get some practice doing problems with parallelogram method and component method.